All right, so we learned about activators. Next up is deactivators. So we can first start off with halogens. Halogens are our weak deactivators. So the induction causes them to be deactivators. They can resonate or they can donate through resonance, but in this case, induction beats out resonance, and that's just experimental. The reasoning behind that is that fluorine is very electronegative, so that's why induction wins out. And then for chlorine, bromine, and iodine, they're very large and much larger than carbon, so they have poor pi bond overlap, and so the resonance is weakened. You don't have to know all that. You just have to know that halogens are weak deactivators. Next up for our deactivators are our pi bonds with an electronegative atom. We'll call these our moderate deactivators. So what I mean by this is something like a carbonyl. That'll be the most common trope. And this R can be many different things. It can just be an alkyl chain. It could be an H for like an aldehyde, an OH for a carboxylic acid, an OR for an ester, or an NH2 for an amide, that kind of thing. Other examples are our SO3H, that's also a moderate deactivator. Cyanide groups will also be moderate deactivators, right? Pi bond to an electronegative atom, that kind of thing. And if we think about why this occurs, first of all, we have induction from the electronegative atom, which I've called Y here, right? That's obviously going to inductively remove some electrons, but also resonance will also withdraw electrons, right? So we could draw a pi bond, leaving the benzene ring to form a carbon-carbon pi bond here. And then this carbon electronegative atom bond can go on to the Y. So in this case, both resonance and induction pull electrons out of this ring. And then finally, we have strong deactivators. And in this case, we have many electronegative atoms or a lot of resonance. So for example, the nitro group is a very strong deactivator. Right, we've got 3 electronegative atoms. And as well, we can draw resonance structures in which we're withdrawing electronegative atoms. Another example is a protonated amine. Right now, we've got a very electronegative atom, nitrogen, with a positive charge that's really going to pull away those electrons. And then finally, something like a trihalide here, right? So these 3 X's are 3 halides, usually fluorine, right? Very electronegative atoms. They're going to pull away the electrons. And simply what you can do here is just Google activating, deactivating groups. And you'll find all sorts of charts on the internet. Here's one of them, right? You can see here we've got our baseline. Over here we have activating, or my bad, deactivating groups. And then over here we have activating groups, right? You can see the alkyl halides are weak activators. And then we get to stronger and stronger activators. You can see that halogens, while they are deactivators, they're relatively weak deactivators. However, note that just because something is deactivated doesn't mean that it can't react. So for example, if we have our benzene ring with some sort of substituent and we try to nitrate it, we can nitrate it no matter what the substituent is. It just takes longer, right? So for example, if your R is just your hydrogen, then if we call that a relative rate of 1, if you had a nitro group, then its relative rate would be 6 times 10 to the negative 8, right? Way slower. A chlorine would be something like 0.033, so still much slower. And then an alcohol would be something like 1,000 times faster, right? So it doesn't mean that this reaction won't happen. It's just going to take longer, or you're going to need higher temperatures. But either way, be able to spot activating and deactivating groups.